Hi viewers, welcome to Lama Solution. Today we are going to see about solar PV EV charging station with the grid integration in the MATLAB. So this is a simulation model we developed for a solar PV EV charging station with the grid integration. So this model consists of a solar PV array, and solar PV array going to be connected to the DC bus. So via this interleaved buck converter. And here you can see that, so this is the rating of solar PV array. The single panel rating is 250 watts, and here we are using 16 series connected PV module in the single string. So totally it can generate around 4000, that means 4000 watts, that means 4 kilowatt at 1000 watts per meter square. And the voltage right across that single panel is around 30.7, and then current of the single panel at maximum power point will be 8.15 amps. So totally here you can see 30.7 into 16. So 30.7 into 16 is around 491.2 volt. Okay, at the PV power point condition, right, the voltage around 500 here. Okay, so this voltage should be stepped down to 400 volt. Okay, because see here we are going to maintain the DC bus voltage equal to 400. Okay, so this 400 volt going to be stepped down to 500 volt going to be stepped down to 400 volt. So for that here we are using interleaved buck converter. So this is structure of interleaved buck converter. So why we are using interleaved buck converter? When you are going to use normal buck converter, right, so it maybe go for a discontinuous conduction mode, and also the ripple in that load current, then output of converter and input current, right, it have more, right. So in order to minimize that ripple current, so here we are using interleaved buck converter. When interleaving that two converter, then that ripple of current will be reduced. Okay, so for that purpose only here we are using this interleaved buck converter, and this interleaved buck converter going to be controlled by means of MPPT algorithm. So MPPT nothing but maximum power point tracking algorithm. So the maximum power point tracking algorithm used in the PV system to extract the maximum power from the PV panel, because here already I show that the detail, the main. So here you can see that for different irradiation condition, that means different sunlight intensity condition, right. So what will happen, that peak power of the PV panel will be varied. Okay, so we must track that peak point, right. So in order to track that peak point, so we need to use some control concept. So the control concept nothing but maximum power point tracking algorithm. So here this is known as maximum power. So we are going to track that maximum power, so that is known as maximum power point tracking control algorithm. So in order to extract that extract that power from the PV, so this interleaved converter, buck converter going to be controlled by means of this incremental conductance MPPT. Okay, so this incremental conductance MPPT receive two inputs, PV voltage and current. So based upon that PV voltage and current, so here we have to initialize 4 parameter: initial duty cycle, maximum duty cycle, minimum duty cycle, and then we have to calculate change in voltage and change in power, change in current, and then based upon change in voltage and change in current, we have to increment or decrement the duty cycle, as well as, so based upon that incremental conductance, so you have to increment or decrement the duty cycle. So this will be keep on executing in order to find out the duty cycle for that interleaved buck converter, for step down the voltage from 500 to 400, as well as extract the maximum power from the PV. So next thing is grid integration. So here we have single phase grid. So here we are using 230 volt AC supply, and the 230 volt AC supply is connected to the DC bus. So common DC bus via this inverter. Okay. So in order to control this inverter, here we have that control logic. So here you can see that we are generating the current reference. So based upon PV current and EV availability. Okay. So based upon whether EV is available or not. Okay. If EV based upon the availability of EV, so we are going to generate the reference current. So here you can see that we are checking the PV current. If PV current is less than 0.5, that means there is no power generation from the PV and EV is enabled. Okay, so then we have to charge the EV via grid. So we are taking power from the grid. Okay, so next, for example, the condition will be changed from this point to this point. Okay, so we are getting the power from the grid to charge the EV. So when the power generation is more than 2 amps from the PV, then we are jumping from this logic to this logic. That means we are not taking any power from the grid. So I reference here we are making 0. Okay, so only thing we have to check that when PV is less than 0.5 amps and then EV is turned on, EV is connected to the system, then we are going to take the power from the grid. Otherwise we are not taking any power from the grid. Is directly and the PV going to be used to charge the battery. So in order to reduce that means in order to avoid that cost of grid purchase. Okay, so after that here we are getting the reference current and then reference current going to be converted into sinusoidal form, and then here we are having alpha beta naught to dq naught conversion. So here we will have dq naught conversion. So next thing is here we are measuring the inverter current. Okay, so here we need to measure the inverter current. So here, and then it going to be converted into dq naught. So by using alpha beta naught to dq naught conversion. So after conversion of alpha beta naught, right, and so dq naught conversion, so actual and reference dq naught, right, going to be compared here and processed via PA controller. And then after conversion, right, we are having controlled voltage in the form of a dq naught. So again we have to convert to alpha beta naught, and then you have to take this first quantity, nothing but alpha, and it going to be processed via sinusoidal PWM. So it will be generate the pulse. So this pulse is going to be used for control this inverter. So based upon the reference current, the inverter, this inverter going to be controlled in the current control concept. Okay. So next we have to move on that EV and stationary battery connection. So here we are using bidirectional converter. Okay. So this bidirectional converter going to be used for connect the battery with the DC bus. That means we have to connect the EV battery with the DC bus, as well as you have to connect stationary battery with the DC bus. Okay, so for that we are using bidirectional converter here, and bidirectional converter will be work on in both direction. Okay, so it will be send the power to the DC bus, or else it take the power from the DC bus. So this bidirectional converter will be operate in both direction when a stationary battery is connected to the system. Okay, otherwise what will be when EV is connected, for example if stationary battery is connected to the system, so here we have some arrangement, right, both EV connected in the common converter. Okay, so if stationary battery, that means EV battery is not presented in the system, then the stationary battery will be connected to the system. If EV battery is connected to the system means, so the stationary battery will be disconnected from the system. So for that we have some logic, that means here we have circuit breaker. So here you can see that, so this is a control logic, that means if it is 0 means EV is not connected into the system. If it is 1 means EV is connected to the system. Okay, so if 0 means it will be generate 0 here, so it will be trip this circuit breaker, and then here we will have 1, and then it will be enable this trip. So then the stationary battery will be connected when the signal will be 0. So stationary battery will be connected to the system, Okay, next thing is when here the condition will be one means, so this strip will be connected and this circuit breaker will be disconnected from the system. So stationary battery will be disconnect, only EV will be connected in the system. Okay, so when stationary battery is connected in the system, right, so what will happen, this bidirectional converter will be act in both directions. That means, so when stationary battery is connected in the system, only the system will be operate. That means the PV power, right, PV power going to be used to supply this local load as well as charge the stationary battery. When PV power is less, right, then what will happen that the battery, stationary battery will supply this load, DC load. Okay, so here during this condition, so the grid never participate in the system. Okay, so when EV is connected, that means this control signal is on, right, then EV will be connected with the system. So during that, what will be happen, when PV having excess power, it will be supply this DC load as well as charge the EV battery. Okay, when PV is less than, the PV is not generating power, then the grid will be supplying power to the EV as well as this DC load. So during this condition, so when EV is connected, during that time grid will be comes to supply the power when there is no power in the PV. Okay, so this is the concept of solar PV EV charging station with the grid. And here you can see that this bidirectional converter going to be controlled by means of voltage control method. So here we are measuring the DC bus voltage and going to be compared with the 400 volt, and then it going to be processed via PA controller. Okay, so this PA controller then is going to be processed via PWM generator and it will be generate the PWM pulse. So this is going to be used to for control this bidirectional converter. So this will be control this DC bus voltage maintained at 400 volt. So next you have to test the system. So here we can measure the storage battery voltage and current, EV battery voltage and current, and here we can measure DC load, DC bus load current and power, and then here we can measure the power of PV, DC load power, battery and EV power, and then storage battery and EV power, grid power, and here we can measure the SOC of the EV battery. So the first one is SOC of the EV and second one is SOC of the storage battery. Okay, next thing here you can see the inverter current and the grid current. Okay, so now the condition is, so we are connected that EV, that means here we are making condition 1, right. So now the EV is connected to the system, so you have to check the response. So and also we are varying the irradiation from 1500 and 0. So here you can see that the PV generating around 4000 watts. Okay, so here DC load is around 1000, and here you can see that the battery current, right, is around 12 amps, and then battery voltage is 250 volt, and here you can see here, right, power of PV is 4000, load will be 1000 and battery will be 3000. Okay, and that means EV battery power, right. So this is the pink color is EV battery power and green will be storage battery. Okay, so based upon that power availability of PV, right, the power is taken from the DC load as well as battery. Now the battery power, right, for 500 watts per meter square, battery power is 2000, so that will be given to the DC load and the remaining power going to charge the EV battery. Okay, so now you can see that now the PV power, right, now PV power is goes to 0. So when the PV power goes to 0, what will be happen, right? So we are getting power from the grid. So here you can see that we are getting power from the grid during this time. Okay, so we can see that the EV battery is still in charging mode, and also this load receive the power. Okay, so here you can see that when PV power change from 0 to 2000 watts, right? So here you can see that we are not getting any power from the grid, it goes to 0, and here you can see that EV battery is in a charging condition on. Okay, so this is when we are connecting EV into the system. So here you can see that the battery current, storage battery current always 0, because when the EV battery is connected to the system, right, the storage battery will be disconnected, and then so it's not taking any charge. Okay, so here you can see this variation of a battery current, and here you can see the variation of DC bus voltage, DC load current, and DC load power. So this is variation of PV voltage, PV current, and the PV power. Okay, so here you can see that, so this is a variation of SOC of the EV. Okay, sorry, once again. Yeah, so this one is SOC of the EV, this one, and this is SOC of the storage battery. So here you will see that SOC will be keep on increasing for EV. Okay, but here you will see that SOC of that storage battery is very, that means not discharging, is having around that means discharging value is around 0.00001, like that only. Okay, so now I am going to change this control logic to 0. So now storage battery is connected to the system, and then you have to check the result. So what happened to the system? Okay, and changing that condition. Now the EV is not connected in the system, EV battery. Okay, now you have to check the results. So now here you can see that, right? So EV is not connected, so that's why the EV battery current is 0. Okay, and then the remaining thing, right, the PV power voltage current will be follow, so it is from 1000 watts per meter square to 500 and 0. So based upon that PV will be generate the power. So now here you can see that, so PV is initially 4000, so 1000 will be given to the DC load, and 3000 taken by the battery. Now is 2000, so 1000 given to the DC load, and then 1000 given to the battery. We will check the result when PV goes to 0. Now we can say PV goes to 0, so because of PV goes to 0, right, so what will be happen, the stationary battery will supplying power to the DC load. Okay, so it is going for negative, so negative in the sense here battery now comes to supply the power to the DC load. Okay, so here you can see that the grid is remains 0, because during when storage battery connected to the system, so the storage battery only used for supplying that local load. Okay, when EV connected to the system, so based upon PV power, right, grid will be connected to the system to supply the EV battery as well as the local load. So this is a concept of this model. Okay, and here you will see that now, so the SOC battery will be remain at 9%, right, and then here you will see that, so that means storage battery, right, first is charging mode, and then is discharging mode, again going for charging, right. So here you will see that you cannot see that 9% is that means charging rate is around 0.001 only, right, it is minimum only. So is maintained at 9% only. So because you can see here, right, current of the EV battery will be 0 in all timing. Okay, so this is working of solar PV EV charging station with the grid system. So grid will be only connected during that when EV is connected for charging. Okay, other time, right, I won't connected to the system, so because of that we cannot we will reduce the purchase cost from the grid. Thanks for watching our video. Kindly subscribe channel and also click bell icon for notification about upcoming videos. Thank you so much. Bye bye.